In this section, we're going to look at average rates of change. And so we'll start with just a basic definition and do just a couple of general examples of this. So the definition is that the average rate of change of a function y equaling f of x between 2 points x equal a and x equals b is denoted ARC for average rate of change equaling f of b minus f of a over b minus a. And so one of the things that should look somewhat familiar with this expression here is this is actually a slope formula. If I think of this in terms of y's, these are the change in y's over the changes in x's. So this is the slope of the secant line between a and b. Okay, so what do I mean by a secant line? Well, if I look at a particular function, generally we don't really care what that function looks like, and I pick 2 points. I'm going to call them a and b here. So I've got this point here and this point here. I can look at the actual curve between those points and figure out that distance using our distance formula. But if I look at the secant line, which is just the straight line that passes through those points, okay, then my slope of the secant line can be found by looking at the change vertically and horizontally. So the change in the y values, so this is going to be f of b minus f of a, so that distance between the high and the low, and this distance, the horizontal distance, is just the distance between the 2 points a and b. So if I look at that ratio, that's going to give me the slope of that dotted line, which is our secant line. Okay? So notice here, it's not going to matter what my function looks like between those 2 points. All I really care about is the endpoints of the interval. Okay? So I could take the same function, and I'm going to mess this graph up a little bit, so hopefully you have kind of written that down or pause it at this point so you can look at that clearly. But if I look at this black curve, I could also have a function that does something like this, where that's the blue curve. And you'll notice, if I look at them, it does not matter whether I'm looking at the black curve or the blue curve, but for those points A and B, these are going to have the same average rates, okay? Because I only care about what's happening at the slope of that secant line between the 2 points, okay? So one of the things you're going to be asked to do in this course is to calculate average rates of changes for different functions. And so I have 2 examples here because depending on the type of function, you're basically going to be doing the same thing, which is evaluate the function at a point and then simplify the resulting expressions. Okay? One example that you're going to see is something like this. So h of t equaling t squared minus 4 on the interval from -1 to 3, which we'll work through in just a minute. But then the other type that you're going to see is something like this, where I've got my function and my interval is what we consider an arbitrary interval. It doesn't actually have numbers in there, but it uses variables to represent the distance that's being looked at. Okay? So let's start with this first one. So for the t squared minus 4 on the interval from -1 to 3, I want to find the average rate of change. So my average rate of change says I'm going to look at h of 3 minus h of -1 all over 3 minus -1. Okay? So to simplify this, I need to start by evaluating my function at each of those values. So h of 3 says I'm going to take 3 squared minus 4. H of -1 says I'm looking at a -1 squared minus 4. And then on the bottom, I can go ahead and simplify because I don't have h's there. So 3 minus a -1 looks like 4. So simplifying the top there gives us a 9 minus 4 and a 1 minus 4 all over 4. Subtracting looks like an 8 minus a -3. And then simplifying looks like 11/4. So my average rate of change, meaning the slope of my secant line for the function t squared minus 4 on the interval from -1 to 3 is 11/4. Okay. In this next example, like I said, the difference here is I'm no longer looking at numerical intervals. I'm looking at arbitrary intervals where my interval values are represented by variables. Okay. Now this one also, the function is a little different. So here I'm looking at f of x equaling x plus 1 divided by x minus 3 on the interval from t to t plus h. So I'm just looking at an interval that's h units long. Okay. The process is exactly the same. So my average rate of change says I'm going to find f of t plus h minus f of t all over t plus h minus t. Okay. And I encourage you to write this out first because it doesn't matter whether my function is polynomial or rational or radical or whatever. Notice here, if I do it like this first, then I can see that my function here is going to involve a rational function over top of some stuff. It's not just a single rational like the last one was. Okay, so my f of t plus h says I'm going to put in t plus h into my equation everywhere there's an x. Minus my f of t, so same thing, put in a t everywhere there's an x. And then on the bottom, t plus h minus t looks like just h. So now comes the simplifying. Okay? Well, to simplify the numerator, I'm going to need a common denominator. So my common denominator here is t plus h minus 3 times t minus 3. Okay. On the top, I need to multiply by the missing pieces. So we'll get a t plus h plus 1 times the t minus 3 minus t plus 1 times t plus h minus 3. Okay. Now it's a matter of multiplying out and combining like terms. Notice the complex fraction here, we can invert and multiply to get that down. So here we'll get a t squared plus a th plus t. Distributing the t through, distributing that 3, we get a minus 3t minus 3h minus 3. Over here, we'll FOIL again. Here again, be careful. Don't forget to distribute that minus sign. So we'll get a minus t squared minus th plus 3t minus t minus h plus 3. And on the bottom, that h we can pull up and get rid of that complex fraction. Now here we can see some things will cancel out nicely. The t squareds go away, the th's go away, those t's, the 3t, and the 3. And so all that's left on the top is a minus 4h. Over that denominator we had. So the h's will cancel out. And our average rate of change looks like a negative 4 over t plus h minus 3 times t minus 3. Okay? So again, the difference between the two. In one case, I'm going to get a numerical value if I'm looking at a numerical set of limits in my interval. If I have an arbitrary interval with variable limits, then I'm going to end up with an expression. Okay? And again, these will take, depending on which ones you're looking at, May take longer or shorter depending on your function. Okay. And so one last thing to note about average rate of change is that if I am looking at a linear function, we get some nice results. Okay? So for example, if I'm looking at, say, f of x equaling a 3x minus 5, and I'm just going to pick a couple of different intervals. So for this first one, let's look at the interval from, say, -2 to 3. Let's look at the interval, so that's one that involves some negative values in there. Let's say we look at the interval from 5 to 10. And then lastly, let's look at one of our variable intervals. Okay? And again, the nice thing to note here is this is a linear equation. So let's take a minute and work through each of these and see what the results look like. So for this first one, if I'm looking at the interval from -2 to 3, it says my average rate of change is going to be f of 3 minus f of 2 all over 3 minus 2. Which when we plug in, at 3 we get 9 minus 5, which is 4. At 2 we get 6 minus 5, which is 1. And on the bottom we just get 1. Okay, so simplifying, we see that our average rate is just 3. For the interval from 5 to 10, if we do f of 10 minus f of 5 over 10 minus 5, same thing, so plugging in 10, we're getting a 30 minus 5, which looks like 25. At 5, we get 15 minus 5, which looks like 10, all over 5. Well, simplifying, that looks like 15 over 5, or 3. And for our last one, the variable interval, our average rate of change is going to be f of t plus h minus f of t all over t plus h minus t. So rewriting there, f of t plus h looks like, and I'm going to go ahead and distribute it out, so if you need to take a minute and look at that, it'll be 3t plus 3h minus 5 minus f of t, which is 3t minus 5, all over h. And so here you can see that the 3t's cancel and the 5's cancel, and we're left with 3h over h, which again is just 3. And so we get some nice results from average rates that are for linear functions. If I have a linear function, then it does not matter what my interval looks like. My average rate of change is going to be the slope. And again, if you think about why that is, remember we defined the slope to be, we defined the average rate of change to be the slope of the secant line. And so if I'm looking at a linear function, so in this case, if I'm looking at a 3x minus 5, it's going to do something like that. If I look at that secant line between any of the 2 points, so let's say I'm looking at those 2 points there, then my secant line is just the line. And so the slope of the secant line happens to be the slope of my function.